Hello everyone, I'm Xuezheng Lu from Northwestern University. Today I'm going to talk about the tunable inversion symmetry to control the indirect to direct bandgap transitions. Before the talk, I first thank the organizer for providing this opportunity with me to introduce my work here. And I also thank my advisor, Professor James Rondinelli, for the instruction in the work. And this work was also supported from the Center for Nanoscale Science. In this presentation, I will first introduce an unusual polar to nonpolar transition in layered oxide by string engineering. And then I will mainly talk about our findings in the one-by-one ultra-short superlattices. That is, there is a competing nonpolar phase under epitaxial string, and also the indirect to direct bandgap transition in the across the transition as shown in the figure below. In calcium titanate 327 layered oxide, the polar to nonpolar transition in either compressive or tensile string was predicted, and which is featured by the changing pattern of out-of-phase oxygen octahedral rotation, in which the in-phase rotation in polar phase is transformed to the out-of-phase rotation in the nonpolar phase. But as studied by the Landau model shown here, we found that the string tunable trilinear related couplings in the two phases can be responsible for the appearance of the nonpolar phase under epitaxial string. To apply our theory to other compounds in the AB0327 family, we find more materials showing such unusual polar to nonpolar transition under epitaxial string. From this table, we found with small tolerance factor, the polar to nonpolar transition can occur in both compressive and tensile string. But with increasing the tolerance factor, only the compressive string can trigger the polar to nonpolar transition. And we also found that the polar to nonpolar transition can only occur in a range of tolerance factor as shown here. And it's very exciting that the PBCN phase in the bulk strontium zirconium oxide has recently been found at high temperature in experiment, which is consistent with our prediction on the temperature dependent of the stability of this PBCN phase. To further apply our theory and elucidate the general feature of a nonpolar phase in hybrid improper parallaxics, we just focus on this one-by-one ultra-short superlattices, which is predicted to be the hybrid improper parallaxics if the PMMA phase of each component can have lower energy. And this work was also concisely discussed yesterday by Professor James Rondinelli. And the work here is based on the density functional theory calculation coded in the Westwood. The PBE saw a change correlation functional is adopted in the calculation. And the way to apply the tensile and compressive string constraints is shown in the figure. And here we applied the in-plane backcell string. And we also use the genetic algorithm structure such method to confirm the ground state structure under epitaxial string. And Landau model and Talabani model are used to explain the phase transition and also the electronic structures in each structure. We then found in the lanthanum yttrium gallium oxide the previously predicted bulk PMC21 phase cannot be stabilized under backcell string. where the P2M nonpolar phase can be more stable in the Hall range studied here. And we also found in the lanthanum, yttrium, aluminum oxide, the P2M phase can also be stabilized up to a tensile strength at 2%. And to further elucidate the stability of the P2M phase under back-cell strain, we also investigated phase stability under the anisotropic influence strain. Here we found with increasing the AORB ratio, the energy of PMC2M gradually goes up, and the energy of P2M will gradually go down, which results in crossover at AORB approximately equal to 1. We then use the Landau model to explain the macroscopic mechanism on the phase transition. Here in the polar phase, there are 3 modes. One is the polar gamma-5 minus mode, and the in-phase rotational mode. The M2 plus in-phase rotational mode, and the M5 minus out-of-phase tilt mode. And in the non-polar phase, there are 7 modes. There are seven modes. There are 4 anti-ferroelectric modes, and M4 minus out-of-phase rotational mode, and also the M5 minus tilt mode, and also the X1 plus tilt mode. And in the Landau model, we have 3. We have 3 parts. The first, which the terms only consist of the polar or antipolar mode, and the terms only consist of the tilt and rotational mode, and the last term only consists of the interactions between the first 2 parts. And the mode, the figure just describing the mode displacement. By comparing the phase diagram from the direct DFT calculation and also the Landau model, we found that this shows the similar tendency of the phase stability, but there is no difference here. We found that the phase transition occurs at 2% tensile strain, versus no transition occur in this DFT phase diagram. This discrepancy, this quantitative discrepancy is caused by the ignorance of the gamma 1 plus mode in the polar phase, and also the gamma 1 plus and X3 plus mode in the nonpolar phase, which will not influence the main, the qualitative mechanism on the phase transition is brought here. We then decompose the energy of PMC2 and P2M into the 3 parts described in the last slide, and then we find the energy difference between the antiferroelectric mode and polar mode just increased, and the energy difference between the P2M and PMC2M phases in the tilt and rotational mode just decreased. The total effects lead to the energy difference between the 2 phases decreased, which means the P2M phase should be stable under tensile strain. But this is in contrast to the results from the 2 figures. And by checking the energy difference between the 2 phases in the anharmonic interactive term, we found it's the strain tunable anharmonic interactive terms. Responsible for the compensate the energy difference between the first 2 parts in the 2 phases, and also lead to the correct phase diagram obtained from the 2 figures. And this mechanism is also applied to the phase transition under the anisotropic strain. And then we studied the electronic band structure in the two phases. Interestingly, we found the indirect band gap in this polar phase, but direct band gap in the nonpolar phase. And yes, before studying the electronic properties, we, as first guess, we expect the valence band edge consists of the p orbital of oxygen because the d orbital, the d shell is closed in gallium, and also we expect the interband interaction between A cation and oxygen, between B cation and B cation and oxygen, may also have effects on the valence band edge, which is verified by the density of states. And here, except the PP orbital interaction, the px orbital interaction, here X means the F and D orbitals, are also important to the formation of the valence band edge. Here we focus on the valence band edge because the CBM is always located at gamma point. And to study the band gap character changes changing between the two phases, we rely on the Tet-Bandy model. Tet-Bandy model here in which the block function can be expressed in terms of the atomic orbital function, and then an electronic function can be a linear combination of the block function, and then we can finally obtain this energy band for this energy for each band at key point can be expressed in as this equation 3. And in equation 3, the matrix is inside of 148 by 148 and includes orbital interactions among the lanthanum d and f orbitals, yttrium d orbitals, and gallium s orbitals, and oxygen p orbitals in this 40-atom structure. And the Van-Neuronati calculation will carry out to obtain the orbital interactions in this matrix. And we then decompose the energy differences between the S and gamma point in the band structure of polar phase, and also the ED and the energy difference between ED and gamma point in the nonpolar in the band structure of nonpolar phase into the PP contribution and also the PX contribution. Then we found the PP contribution can be positive, and the PX contribution can be positive, and the PP contribution can be negative. We also found in the polar phase, the PP contribution dominates, and in the nonpolar phase, in the polar phase, the PX contribution dominates, and in the nonpolar phase, the PX, the PP contribution dominates, which just leading to the indirect band gap in the nonpolar phase and the direct band gap in the nonpolar phase. And we also, is there any? Okay. We also studied the mode effects on the, on the band structure, on the energy differences between the S and gamma point in the polar phase, and also the ED, also the energy difference between the ED and gamma point in the nonpolar phase. And the main conclusion here is the larger oxygen octahedral rotation mode in the equilibrium structure will favor the indirect band gap in the superlattice. I want to start it. This is okay. And we here we just obtained the talk about the conclusion and no discussion. And here conclusion is the tilt and the rotation controls will compete with the lattice parameter change. By we studied many materials in the polar phase with substitution of different A side cation or the B side cations to obtain this conclusion. So if you want to obtain, we finally obtained the increasing the tilt and rotation and also decreasing the lattice parameter, it will favor the indirect band gap in the polar phase. And this is the, the design rule we just obtained by collecting the result from the material we studied here. And this is the conclusion.
or maybe one or two short questions? No. With that, I think we're time limited here. So we bring the next speaker up, please? Thanks.
Thank you.